So it's going to be very unorganized because I really don't have any particular material, but I'm trying to going over those reactions, the mechanisms that we have discussed in OChem 1. So this is almost like a review sessions, and I think you're probably going to need it, especially for the problems that I posted it for those PLTL problems for alcohol synthesis. Those are kind of open-ended questions, and there could be a many different way, but at least you gotta know your reactions to make right choices. So I like to first going over the OChem 1 reactions and mechanisms and things that you probably need to remember, and then I guess we'll go from there. So let me first share my slides. I got blank slide basically, so I can write on it. So nothing there. Anyway, when you have a question, just feel free to stop me. Um, okay, the switching pen to laser pointer is going to be a big issue because of my home. I didn't really have this set up yet. But anyway, okay. So, oh, so you told me that you cannot see pen, right? You can only see the writing, not the where I move the pen on the screen.
Yes, that's correct.
I'm moving the pen, but I guess you don't see anything until I actually mark it on the whiteboard.
Yeah, nothing showing up.
Yeah, that's just keep back and forth of this pen and laser point option. Just keep make a make a mistake. But anyway, I'll manage it. Well, let me just go really briefly on the reactions in OChem 1. I think you really need to remember. Those are chapter 6 reaction, those are substitution reaction, right? Substitution reactions and elimination reactions. So what did we talk about substitution elimination reactions? We have talked about alkyl halide, right? There's a variety of different types of alkyl halide. I'm just going to write down very simple one, the ethyl chloride here. And then you can react with a strong nucleophile. And what happened was this attack this carbon and then kick the leaving groups out. So we're going to have a substitutions. And these reactions typically requires a strong nucleophile, right? We need to have a strong nucleophile. That's what is needed. But if you do this reaction with a nucleophile with a strong basicity, then there could be something else can happen. So let me just put it down here. If it is a base, somehow base is also carrying the negative charge. So what makes a strong nucleophile also makes a good base as well. So this is sort of like a dual properties. Unfortunately, we cannot just designate a molecule that, oh, you're going to be acting only as a nucleophile, only as a base. So if the reagent has a nucleophilicity and the basis at the same time, then there's a potentially the two or more reaction can happen at the simultaneously. So but just trying to describe, this is an SN2 reactions. If the base comes in and then what's the base job of the base is not making a tag, it pick up the hydrogen in adjacent carbon, and then this basically make the electron pairs go in between the carbons, and then we're going to have a leaving group goes out. So we're going to have a elimination reactions. That would be the E2 elimination reactions. So that was something that you remember that was a discussion from the chapter 6. So I'm going to write down the chapter 6 right there. And at that time, we also talked about there's another mechanism, which is something, maybe I should use secondary. So the primaries are not really good subject for the elimination reaction, E1. This is a situation I was thinking of. What I'm trying to describe is a E1 and an SN1. So E1 and SN1, there's a solvent there. Typically, the solvent is not something you would consider strong nucleophile, strong base. This is going to be weak base, right? And this is also going to be weak nucleophile. So SN2 will not happen, E2 will not happen. So most likely there's nothing happening until the halogen basically take off. So when the halogen goes out, so let me switch the pen color. Where's the blue? So I probably have to write down blue color down there. So if the halogen takes off, what happened was it produced the carbocation, right? And then carbocation, there's a few things could happen. The solvent molecule, I'm just gonna solvent here. If it is a reaches lone pair, captures it, then we're gonna have a solvent molecule sitting on there. That's basically SN1 reactions. If the solvent molecule is acting as a base and then it's picking up the hydrogen in adjacent carbon, then that's going to go for the elimination reaction, and then we call it E1 elimination reaction, right? So there is a this is a sort of like things can happen to the alkyl halide depending on what they're reacting with. But the most time you have to make some choices based on the what you are actually reacting with. So I'm trying to go for that part. So let me switch the color. So I don't want to make it too complicated here. So the photon-SN2 reaction, what is a really important photon-SN2 reaction is a strong nucleophile. That is something that we must have. At the same time, what is an SN2 reaction is really, really sensitive to steric hindrance, right? Steric hindrance. So because of that, we need a strong nucleophile, and then we probably prefer something that is not too hindered nucleophile, so something small. At the same time, alkyl halide side is also we need something more accessible, like a primary alkyl halide. I mean, for that reason, if it's an alkyl halide side, the primary alkyl halide it works really great for the SN2 reaction. Secondary is sort of okay, but tertiary, I would say tertiary is really, really not good for the SN2 reaction. I hardly see tertiary alkyl halide going for the SN2 reactions. But not only that, the nucleophile also has to be small. So that is a one thing. For that matter, E2 elimination reactions, the alkyl halide actually go for a different trend. Because of this is a lot of electron movements. You base pick up the hydrogen, electron moving over there, making a double bonds, and kicking the halogens out. There's a lot of things happening, and then the more the alkyl chain goes, it actually becomes a more stable alkene formation. So alkyl halide side, what the E2 reaction prefers is a tertiary alkyl halide, which is a better than secondary alkyl halide, which is a better than primary alkyl halide. So if you're looking at the what is called the alkyl halide side of the reactions, then you can clearly see that they are requiring different things. Tertiary alkyl halide, if there's a equal possibility the reagent can acting as a nucleophile or base, tertiary alkyl halide will prefer E2 elimination reaction. But if it's a primary alkyl halide, it's going to prefer SN2 reactions, right? The problem normally happens for the secondary alkyl halide because secondary alkyl halide is sort of like it can go SN2 reaction. It can also go to E2 elimination reactions. So that is a sort of like a very gray areas. You will actually not sure what's going to happen. Then if somebody asks me what's going to happen, I would say maybe both will happen. You may have a some SN2 reaction, you may get some E2 elimination reaction. So those are something that can happen to secondary alkyl halide. So secondary alkyl halides have to be somewhat careful. But there are other factors that also determining the fate of the secondary alkyl halide. So that is also the reagents. I mean, we also talked about the strong nucleophile prefer the SN2 reactions. Strong base, I should probably also say that strong base prefer the E2 elimination reaction, right? Where's my pen? Where does it go? Okay. So it has to be a strong base too. So even though it's a secondary alkyl halide, if your reagents are strong nucleophile, not a strong base, then you will get most likely SN2 reactions. Even though it's a secondary alkyl halide, you get the reagent that is a predominantly basic, non-nucleophilic, then you will get the E2 elimination reactions. So you can narrow further down the choices by the nature of the reagents, not only the alkyl halide. that was a sort of like a very tricky part of the chapter 6. But let me just talk about several examples of some of the strong base, something we can all you can assume that it's going to be a strong bulky base, so that it doesn't participate in SN2 reactions. So strong bulky base that, let me put down here, strong bulky base. So strong bulky base, because of the bulkiness of the reagents, these will not participate SN2 reaction easily. So what are the example? Something like a butoxide, that would be three methyl groups on T-butyls is quite big, so it makes this T-butoxide not a good nucleophile. The other thing called diisopropyl amide. I mean, it could be nitrogen negatively charged, or even though it's a neutral amine, still two isopropyl groups makes a huge presence. So there are something we can consider bulky base. There are other things called the triethylamine. These nitrogen lone pair, that's the one makes it basic. But three alkyl groups, three ethyl groups are basically it's pretty big size, and then that's why this doesn't normally go for the SN2 reactions. Some of the pyridine analog, pyridine is not really I mean, it's a somewhat nucleophilic, but not. But if you put a methyl surrounding those nitrogen, then that's even more bulky around the nitrogen section of the pyridine. So that can something you can consider strong bulky base. So these base is going to be sort of like uh, select the reaction will go for the E2 elimination, even though there is a possibility of SN2 with a small more reagents. But that would be something that we talked about. But what about SN2? You want to do an SN2 reaction to a secondary alkyl halide, then the most likely secondary alkyl halide. I mean, if you're reacting with a reagent, some are basic and some are nucleophilic, then both can happen. Then, and obviously it has to be the right choices. Some of the nucleophile is something that you may consider not basic. So I'm just trying to give you the example of the not basic strong nucleophile. Well, first of all, the azide. The azide, if you look at the structure, is like this, right? That's going to be positive. So that is a very resonance stabilized negative charge anion, and then that is something we consider strong nucleophile, but not a strong base. And under the same line, the cyanide is also very strong nucleophile, but it's not a strong base. And some of the, if you think about methoxide like this, right? The methoxide, that's a classic example of that can be good nucleophile at the same time strong base. But if you change an oxygen to a sulfur version, like the thiolate, and if it becomes a sulfur, then this anion becomes somewhat more stable, so the basicity goes down. So this could be a very superb nucleophile, because if you remember the nucleophilicity, what's the matter is polarizability. What that means is it's a soft, big, and then so you can actually squeeze into the small areas and attack the carbon like a sulfur, which is better than hard ball of an oxygen anion. So this type of thing, the sulfur anion, that is something we can consider. I mean, it is a mildly basic, but more basic to the azide or the cyanide, but at least this is not as basic as an alkoxide or anything else on like amide, nitrogen anion, something like that. Those are there could be some other example, but if you have something like this, these reagents are something you can consider not a strong basic. So it has a very good nucleophilicity, but not a strong basic. So even the secondary alkyl reacting with, I would normally assume that'll probably makes an SN2 reaction happening. And then the trait of the E1 or SN1 is basically no strong reagents. Anytime there's a strong reagent, the reaction will happen either SN2 or the E2. E1 on SN1 is basically is not their first choices. E1SN1 happened because this is sort of like their last part, the fate of the reaction, because SN2 cannot happen, E2 cannot happen. The molecule basically sit around, and then if you provide enough energy, then halogen pops off and then make the carbocation, and then both SN1 E1 we normally assume they take place at the same time. So there's no such a thing as you only going to see the E1, you're never going to see SN1, right? They always happen both at the same time. But what is a tricky part, of the E1 and SN1 is always the carbocation, right? The carbocation, they rearrange. So I'm trying to show you what sort of the situation we talked about as a rearrangement, right? Something like this. If you have a chloride here, and then sort of like you put into the water and then you heat it up and then leave it long enough, then waters are not a good nucleophile, so it will never start the need to elimination or SN2 reactions. So what happened was, this is probably not a good example. Maybe I'll use this one. And because the primary alkyl halides are not really going for the E1 elimination that easily either. Secondaries are, tertiaries are really good, but secondaries are at least, marginal. So like a secondary alkyl halide right there. So in the water, so this one will take off. Then you get the carbocation right here, right? This is a secondary carbocation, which is this is okay, but if you can move the hydrogen from the neighboring carbon and with more substituted side, then which is that's a hydride shift, then you can have a more substituted carbocation, which is a tertiary carbocation right there. So this is a basis. This is the reason why the hydride shift. Then why only the hydrogen move? Why not carbon move, right? If the carbon move over there, then if somehow you put the methyl groups moving out, then you're gonna have the the secondary carbocation. So that actually doesn't make any sense, right? If you start from the secondary carbocation and then you move the methyl, then you get the secondary carbocation. So this is energetically, this is basically wasting energy. They're not gaining any stability by doing this type of work. So I don't think this will happen. But anyway, tertiary carbocation, and then that can go further than SN1, they can go for the knee one. Those things are something that we now know it'll happen, but the rearrangement. So basically, the more substituted side, hydrogen can move out. But there's another things can happen. Other thing can influence the rearrangement. Something like, let's say, you got same chlorine there. You put into the water and you heat it up. Then basically chlorine goes out. Then you get the carbocation right here. Um, it will never move from the less substituted side, because if the less substituted side it moves up, then you're gonna get even less stable primary carbocation. So that is basically very counterintuitive. It's the hydrogen, and by moving from the one place to another, it's gonna take energy. So you basically spending energies, and then even got into the worst situation. So that is not going to happen. So that's why you have always moving into the from the more substituted side. But even this is a hydrogen, the secondary position. So if that moves up, then basically you get the carbocation moved to the secondary position also. This is secondary to secondary. So almost looks like this is no gaining any energies. But something that you really have to see here is when the hydrogen move here, that will makes a secondary carbocation that can be resonance stabilized. So resonance stability is something that you really have to keep in mind. For that, and then you have to remember that these resonance structures neither are actual structures. That means that both possibility exist, and then reaction can happen. If the water is capturing it, let's say water capture this carbocation, there's a possibility this water capture this one, or it can all capture that one. So either side, it can happen either way. Then it'll produce a different products. That's rearranged SN1 product. If the water captures the other one here, then that'll basically makes different structure. It is also an SN1, but this one is definitely also from the rearrangement, but we can assume that this will be probably forming more than the other, or because, let me switch the laser point. It's all because if you look at those two resonance structures, we would think these are more major contributing than the other, because this is a allylic and secondary, but if you get that one, that's a allylic and primary. So stability wise, these are more stable. So we assume this will produce more than the other, even though both of them are produced after the rearrangement. Still, there's some of the energies of those intermediate you need to compare if you are asked to pick the most abundant products. But this is just an SN1. E1 elimination can also happen too. So let me switch the pen. So E1 elimination reactions, now probably better be have a different color. Where's the red? So E1 elimination reaction, now the water molecule is going to be acting as a base. So this is a rearrangement happen, and then there's only the one adjacent position here. So I mean for this one, so water molecule pick up the hydrogen, makes a double bonds, so that will basically produce something like this. I mean, this is a situation that you can only have a one potential products for the knee one. But let's talk about this one. If the elimination can happen also before the rearrangement, so mostly, I mean, this is definitely less likely, but at least it's going to give a different types of products. So there's a two hydrogen there. If that picks up the hydrogen from here, and that's going to produce double bonds in these positions. If this water molecule pick up the hydrogen in this position, that actually make the exactly same products after rearrangement happen. So that means that this will be really the major, one of the major products of elimination. This can happen, but that's going to be the minor products. But the point is the elimination, if there is a carbocation there, right, the carbocation there, the hydrogen in adjacent carbon, there is a if there's a two different hydrogen adjacent carbon, then if this one leaves, then you get the one types of product. If that one leaves, you get another products. So that's going to be increasing the number of the products. So that is something that you got to be thinking about for the elimination reactions. I know I'm spending time on something that you may already know, but uh, this is SN2, SN1, E2, E1. Those are the very tricky parts. So I just want you to remember what we went over. And then now I'm trying to go over the reactions in the chapter 8. So chapter 8 is the double bond related reactions, right? If you have a double bond like this, and then we can add a lot of things to double bond by something called the electrophilic. So electrophilic
I have
addition
a
reaction.
I have a
Yeah,
question really
sure.
fast. Regarding when you do E2 using or when you use a sterically hindered strong base and you
Yeah.
are preferentially performing E2, I remember learning that you also more likely get the less substituted product, the Hoffman product, over the more substituted product. Is that
Okay.
true?
Um, so I'm already start writing on it. Let me use this part talking about that one. So you are asking when the Hoffman products happen, when the Saiche products happen, right?
Right.
Sort of. Yeah, I know the Hoffman products is sort of like a somewhat confusing because this is I would say, very special circumstances. The substrate has to be hindered, alkyl halide has to be hindered, and then the base also has to be bulky base as well. You have to have those two big bodies comes together, and then you can expect the Hoffman products. Other than that, it's going to be most likely side chip products. So let me give you some examples here. Um, if you have uh, I'm gonna say like this. So let's say this is secondary alkyl halide, right? And then you treat um, methoxide. which is a base. But if you do this reaction, then I would say you are going to get predominantly just the side chain product because this is a small base, and then this is secondary alkyl halide. So there's a room to this base to come in and pick up the proton. So if that happens, then proton's gonna go, bromine's gonna leave, and then you get the side chain products, right? And what I'm thinking about here using this example is increasing the size of the base. So now we're going to use a T-butoxide. T-butoxide is something that we expect bulky. So if you're using T-butoxide, then do we going to get the Hoffman elimination? I mean Hoffman products? No, still the secondary alkyl halide. There's a room to sneak in, get the hydrogen the same way. So this will actually produce the same side chain products. Then, then when the Hoffman products actually happen is, let's say this, and then I'm gonna make that position tertiary alkyl halide, right? And then I'm gonna make this size sort of like a big like this. So this is now the tertiary alkyl halide, and then even you using tertiary alkyl halide, but if you're using the small base like this, then still it's going to happen on the side chain products. That we don't expect um, any of the Hoffman products with a small base. But if the big alkyl halide, I mean, tertiary alkyl halide with a steady crowded it, then you're using like a T-butoxide. So those are, I would say just too much big bodies in the system. It just somehow bad complementary situations. Then now these cannot come to that side. So only thing it can do, it can go for more accessible hydrogen because that's the only thing that it can go there and get it. So this is a situation that you are going to get the Hoffman products. So it has to be bulky base. Without the bulky base, I don't expect the Hoffman products happens. It also has to be very sterically hindered, like a tertiary alkyl halide, and then hopefully some more bulkiness around it. Then that particular situation, you get the Hoffman. Other than that, most likely the side chain products. So I
Got
hope
it. That
that
makes sense. Yeah.
yeah. So treat the Hoffman very special circumstances. Don't expect the Hoffman happen as common as a side chain.
Got it.
Okay, oh, that's a good point. I just almost forgot to mention that. And now moving on, the electrophilic addition reactions. The reason for the electrophilic addition reactions, the pi bonds are somewhat nucleophilic, right? So if you have the classical example we talked about, HBr, then proton, I mean, I shouldn't write the HBr this way. HBr is a more likely deionize like this. So pi bonds gets the proton, and that if the hydrogen goes there, then you get the positive charge on the more substituted side, not the other way around. And then the negative charge capture the cation, then you will get the substitution products. So this is something we talked about. We add a H and Br to the double bonds, but the bromine going to the more substituted side. So this is a Markov-Nikov products. So but if you want to do that in other way, so if you want to do an HBr, if you want to add an HBr in different condition, like an HBr there, but you add a peroxide, I say hydrogen peroxide. The the oxygen bond is not that stable, so it can if you give it a hit, it can break down and then break down to the hydroxyl radical, and then this hydroxyl radical get the hydrogen from this HBr, then you are actually producing bromine radical. And then the bromine radical now is going to be react first to the pi bonds. So what happened was in the previous example, we add hydrogen first when you're using HBr in just normal way. Proton is added first, and then that goes to the less substituted side. But if you do the radical condition, the bromine radical add first, and then that will make a radical. But the point is the bromine is added first. And this one is basically go for the abstracting hydrogen in the second propagation steps, and then that produce HBr addition, but orientation of the bromine and hydrogen is a reversed. Now we are the bromine on the less substituted side, hydrogen in the more substituted side. That's anti-Markov nickel products, right? So this was a sort of like a situation we talked about. But in either way, if you look at the word intermediate happen, it always happens on the more substituted side. So either Markov nickel products or anti-Markov nickel products, the order was changed because of the what goes in first, but they all produce the more stable intermediates. It just, in the case of the radical condition, the bromine just happened to go first. That's why it makes an anti-Markov nickel products. Anyway, I'm just trying to remind you there. For the alcohol formation reaction in chapter 8, what reaction we talked about is a hydration reaction, right? The double bond, we can add water, but simply just putting into the water acidic water, that is something you could also do, but I would imagine that the yield is not really good. I mean, what could happen was the proton is going to be get by the pi bonds, and then hydrogen go to less substituted side still because the carbocation go to more substituted side, and then that's captured by the water. Then you could have a alcohol formed, and then this is a Markov nickel products. But why I don't think this reaction happened well, if you're using this double bond molecule, that's an organic molecule. They don't have a good solubility in water. I mean, it's acidic water is almost like you dumping the oil into it, and then you're hoping that they mix together. Physically they don't go along well if oil and water does not mix well. So the chemical reaction only happen when they are basically right next to each other's. But if they're physically separated because of their phase is not homogeneous, then you don't expect the reaction happen. So because of that, it's easy to write as an answer. Just putting into the acidic water to double bonds, and you can get the hydration reaction. Is really hard to carry out in reality. So if you want to do that, that's why other people made other reagent called the oxymercuration, demercuration, right? So mercury diacetate. The mercury diacetate is basically breaks it down in solution, and one of the acetate remain there, and then that becomes like the mercurium ion, which is a soft cation, so Lewis acid. So pi bond get the Lewis acid, then you get the mercury sitting on the carbon. In this case, it's not just sitting on the one carbon, it's going to sit on the two carbon because the mercuries are somewhat big enough to cover both of them. So this is initially what happened. But since the mercury is a positively charged, it's going to withdraw electron density from those two carbons sitting on it. This carbon is going to lose electron density to the mercury. The other carbon is going to lose electron density to the mercury, but we expect that the other carbon will lose more because of these more substitutions there. So even though there's more substituted, more carbocation forms on the more substituted side, that can be somewhat more stabilized because of that the more numbers of alkyl substituents. So because of that, if the water molecule see this type of uneven the electron deficiency on those two carbon, they're going to be more attracted to the more substituted side because they're more positive charge, and then the mercury goes to less substituted side. Water is going to sit on the more substituted side. Eventually, this is the first step, right? This is the first reagent. Second reagent, sodium borohydride, comes in and they replace the mercury. Then you get hydroxy groups on the more substituted side, and hydrogen that came from the sodium borohydride sitting on the less substituted side, which is the same, the Markov nickel products. So this is a two-step reaction, but the mercury acetate has a good solubility in organic solvents. And then obviously we still have to add water to the organic solvent, just trace amount. We don't need too much water. A drop or two should be good enough. So it's not like we're dumping into the water there. It's just the organic solvent and then just a small bit of the water molecule that can be at least admissible. And then that will basically make this reaction happen, and then we get the same Markov nickel product because the this reaction is water molecule has to attack this mercurium ion from the backside, but it's going to attack the more substituted side because there will be more carbocation characters. But on the other hand, if you do this reaction in other reagents, something called the borane, the borane is more like aesthetically demanding. Hydrogen and boron will be added together, but hydrogen is going to be pointing, I mean, aligned to the more substituted side, and then bigger BH2 is more aligned to less substituted side. It's all most likely the static reasons. And then these two are going to be added at the same time. So we're going to add a hydrogen on the more substituted side, boron added the less substituted side at the same time. So this is a syn addition. In the case of the mercury, the the oxymercuration, demercuration, there's an anti-addition because of the water molecule attack from the backside. I probably shouldn't write the arrow this way. Because the mercury covers one side of double bonds, then the water molecule has to come from the opposite side because that's only open spaces. But hydroboration, the hydrogen and boron goes on the same side. And then when it's added, you see that hydrogens are sitting on the more substituted side, boron on the second step, which is oxidative walk-up. So hydrogen peroxide and sodium hydroxide will replace the boron to an OH. Then if you look at that one, now the OH is sitting on the less substituted side. Hydrogen go to the more substituted side. This is an anti-Markov nickel products. So this was I remember that the very this brings a lot of this makes a lot of questions asking what types of hydration product you will get, and then these type of choices of the regiochemistry, where the hydroxyl group gonna go, or where the hydrogen gonna go, right? That that depends on what reagent you use. At the same time, the stereochemistry can also be a concern. So I'm going to talk about this stereochemical issue of something else. Let me switch back to the pen again. And I'm almost getting there for the review of the chapter 6. I don't want to talk about too many things. Oh yeah, I still have to talk about a few other things. But um, let's talk about this situation here. Let me use this one here. If this one, and then let's say I'm going to do this reaction like a bromination reactions. If I do the bromination reactions on a Br2, it's sort of like a Br and Br bonded together. Pi bonds makes an attack first and then kick the bromides out. So it's going to make a sort of like a brominium ion. Bromine is sitting there, but since the bromine is big, it's sort of like a still covering both uh, carbons. I mean, why did I put the bromine on the top? I mean, can bromine cannot go underneath? And then yes, they can also go there. I'm just writing the one. I mean, these and two of them will happen together, but I'm just gonna use one of them for drawing out the mechanism for that sake. But we can also expect the other also happen too. For this, there is a kind of a different reaction we can expect. If we do the bromination reaction in solvents like a non-nucleophilic solvents, what are the non-nucleophilic solvents? Something doesn't have any lone pairs at all. So like chloroform, CHCl3. I mean, the like oxygen lone pairs, nitrogen lone pairs. So those are non. If you have a solvent like this, which is a non-nucleophilic solvent, then only nucleophile exists is a sort of like a bromide left out, and that can come back and makes an attack. Now the question goes, oh, which carbon is going to attack and where it's going to attack? So that's something that we need to talk about. It's almost same situation. Bromine is going to, this is a brominium ion, so it's going to pull electron density from both carbon. But it's going to be pull electron density unevenly. Which carbon will lose more electron density? The more substituted side. More substituted side will lose a more electron density. And so this bromide left out most likely going to attack the more substituted side, but because the brominium ions is on the top of the molecule, these bromides should attack from the back side, which is the bottom of the screen. So that happened. Then these methyl groups is on the bottom of the screen, that's going to move to the top because we need to expect the inversion because it's sort of like a backside attack. So, and then, but these, the brominium, the bromide, that's the one that came from this nucleophilic bromide. And then the bromine on brominium ion, that is going to be just moved to the next carbon over there. So even though we got two different bromine, I want you to remember that the incoming bromide that is attacking the more substituted side, and then because of the backside attack, it could also possibly bring some inversion of the stereochemistry right there. And but this bromine, and then this bromine, there has to be anti, or we should say trans, right? Because it's a backside attack. But what if you do this reaction in not in the the non-nucleophilic solvent? Let's say, what if you do this reaction in the nucleophilic solvent, something like alcohol? Let's say I put alcohol there. Then the choice is, I mean, brominium ion will, I mean, this brominium ion will form just the same, but now the system have another choice of a different nucleophile, like methanol. I mean, methanol, it's not a good nucleophile, but being a solvent, that means that you got outnumber the bromine. So this has a higher, better chance to have an attack that than just a small amount of bromide left out going back for the target. So if you do this reaction on the nucleophile solvents, then you will get same, almost same thing, because that kicked out, that is the same. It's going to go for the same position. So, but the alkoxy groups is goes on there, still going to get the stereochemical inversion of the methyl groups because it's a backside attack. And then bromide sitting going for the less substituted side. So still, those two is going to be trends. It's just that now that you're going to have a different thing sitting on it. And that is a sort of like I mean, why did I use this? I should probably better use a water. But anyway, these are halohydrin reaction. If you're using a water, I mean, the methanol will do the same thing anyway. You get the hydroxy groups on uh, the more substituted side, and then the bromine on the less substituted side, and that is a halohydrin reactions. Um, what is something that we need to talk about is oh yeah, epoxidation. And then as we just talked about, there is a different way of making epoxide. These can make an epoxide by the peroxy acid, anything with a 3 oxygen, not 2, 3. So peroxy acid, they will produce epoxide. I mean, just ignoring it will make both enantiomer at the same time. But let's say the hydroxyl groups, I mean, epoxide there, and then methyl group goes down is a one possibility. The other one is definitely oxygen goes in the bottom, and then this one. So that's what I'm saying is the two enantiomers will be produced at the same time, but for the argument's sake, we're only going to just using one. But that's the one way of the making epoxide. If you have double bonds in the peroxy acid, that makes an epoxide. But if you having this halohydrin reaction, what you could do this, you just treat the base like a sodium metal or the sodium hydride. What the sodium hydride, sodium metal does, it'll remove this hydrogen, and then that basically makes an alkoxy groups produced right there, right? We get the methyl still hanging there. And then the bromine happened to be on an opposite side. So it's sort of like now it can kick in. It's a backside attack possible this way, and it moves out, and then these produce epoxide too. So this is kind of a interesting way of the making epoxide. I mean, you can make an epoxide from the peroxy acid, something like the MCPBA, or you can do the halohydrin reaction and then treat the sodium hydride or sodium, so you can make an alkoxide and then make the backside attack. Then you can make an epoxide that way too. But what we really need to talk about, as we discussed in the class, if you make an epoxide, then what can you do with it? And what sort of things you can do with it? So where's pen? Oh yeah, there we go. So let's say you have an epoxide produced like this. Then if you treat that in an acidic condition, proton there, and then I'm going to use methanol because if you put the water, then it's going to be almost same as just the epoxide opens up, also makes it water. So I'm trying to distinguish where the nucleophile is going to go. If you do that, then it will be protonate first, right? When oxygen get protonated, then it will pull electron density from both carbons. Once again, we're going to have an uneven electron deficiency on those two carbons, which is connected to the protonated oxygen. More substituted side will lose more electrons. So that's the where it's going to be the incoming nucleophile is more attracted to. So this methanol is not a really good nucleophile, but we have a protonation done on the oxygen that enhances the electrophilicity or electron deficiency of this carbon. So this is a where it's going to make an attack. Once again, this is a backside attack. So in a way, this very resemble the halohydrogen reaction we just talked about, except this is a positively charged oxygen rather than the brominium ion or chlorinium ion. So this makes an attack. This nucleophile in acidic conditions attacks a more substituted position, right? And then it's also backside attack. So this basically puts methanol methoxy groups in here, and because of that, these methyl groups is a backside attack, so it's an inversion of the stereochemistry happen to these positions. So that's why the methyl goes up. But this basically opens up the epoxy groups. Now the hydroxyl groups are sitting on the less substituted side. So these hydroxyl groups are coming from these epoxy groups, and the incoming nucleophile is sitting on the more substituted side. Once again, those two are the trends because it's a backside attack involved. But if you open the epoxide other way, let's say, let me switch the pen color here. There is a red one. So if you open that one, it's sort of like a sodium methoxide. If you open this one sodium methoxide, or maybe I should redraw here because that's already, oops, that's already messed up. So I'm going to just redraw whatever we had before. This one, now you treat the methoxide here, then it doesn't, we're not going to get a protonation because this is a basic condition. There's no proton to give to an oxygen, but this is a strong nucleophile. So what we can expect, this attacks directly, but because it's a nucleophile, it's sensitive to the steric hindrance. It will not approach to the more substituted side because of the steric hindrance is greater on the more substituted position. So it's going to go for the less substituted side, and then it has to be the backside attack. That part is the same. So now the methoxy group is going to be, oops, it's going to be seen on the less substituted side. It's a backside attack because the epoxy group's on the top, the methoxy side is on the bottom. Now it opens up, right? That means this oxygen still remain on the top, but it's going to be OH once you pick up the proton from the water. And then these methyl groups still sit there. So we're still going to get the trends, but you can see that these two products are somewhat very different. So these are something that we really want you to remember from the chapter 8, because the epoxy is somewhat very useful, but depending on how you opens it, it actually produces a different thing. There are other reaction of the making diol with a maybe something that we should talk about briefly. And I really want to solve some problems. I don't want to speak too much of these things. But let me just go quickly here. You get a double bond like this, right? Then if you treat the permanganate, depending on how you do it, like if you do the cold and dilute, then you're gonna have two hydroxyl groups added there. It's gonna be the cis to each other's, so that's gonna be syndiol. There's the same thing can happen by the other reagent, osmium tetroxide and hydrogen peroxide will do the exact same thing. Why we use a permanganate? Because the permanganate is less toxic than osmium. Osmium tetroxide is a really toxic reagent, it's much more expensive too. But if you do that, the potential manganate, not cold and dilute, it's going to be hot and concentrated. Then what happens is we're going to break it down. We're going to break it down, and then that's going to be a ketone in this particular situation because we got two alkyls substituted. But what if you got a substitution? One side is just one alkyl groups, the other side is a two alkyl groups there. And if you treat that with a permanganate and then concentrated condition, then the singly substituted side will become carboxylic acid, right? That's something that we know. I mean, it's initially aldehyde is going to be produced, but that's going to be further oxidized by the permanganate that we use in the solution. Then eventually you get the carboxylic acid. But doubly substituted side will basically become the same as a ketone. The same thing, but if you're using like a ozonolysis, ozone will break it down just the same. But if you, depending on how you treat it, we only talked about in the book the reductive walkup that can be done like dimethyl sulfide, or you can use a zinc in acetic acid. Then the singly substituted side will remain as an aldehyde, not the carboxylic acid. So that is something that I want you to remember. Double bond can be cleared, but depending on how you do it, or which reagent you're going to use it, you can either producing carboxylic acid like this, or you can have a aldehyde for the singly substituted side. But for the doubly substituted side, no matter what you use, you're always going to get ketone like this. So that part doesn't changes. Um, since there are only a few, like 20 minutes left, there are some reactions in the chapter 10 I think we probably should review, but that's pretty simple, right? Maybe just give a few examples here. One of the things I really want you to remember here is that this is a kind of tricky one too. Now, the reaction in chapter 10, that is like a carbonyl reacting with some kind of a nucleophile, right? Then the nucleophile attack the carbonyl. Why the carbonyl is getting attacked by the nucleophile? If you look at that, oxygen is a very electronegative atom. So it's going to be partially negative. That means that this carbon of the carbonyl is electron deficient. That's where the nucleophile makes an attack. That basically makes this lone pair of, pi bonds of the oxygen goes up after it reacting with the nucleophile. And then if there's a water molecule there, then it basically captures the water and then it becomes an alcohol, right? So that's the general reaction. What is a nucleophile? Well, if it's a Grignard like this, and then this is a carbon nucleophile. We also talked about the organolithium. That would be the carbon nucleophile. But if it's something like a hydride, aluminum hydride, hydrogen, this is a lithium, aluminum hydride. Then is a hydride is going to be the nucleophile. We also talked about sodium borohydride, right? 4 hydrogen on boron, and this time sodium is a salt, and then this is a hydride. So that, depending on what you use, we're going to add that. But this is somewhat easy enough for you to remember. But there's another sticky, kind of a tricky one, which is an ester. Let's say you have an ester here, and then you are reacting with a Grignard, methyl Grignard reagents. I mean, esters are something you have to be careful. It could be happening with an ester. The same thing could happen to like acid chloride, something that can leave when they have leaving groups. So difference, oops, what have I this done moving? Is let me show you here. It's a something like a ketone here, and using the magnesium bromide, then this will make an attack, and then it's going to push it up. So you're going to have a methyl groups attack there, and then this is going to be O minus, and then there's nothing to leave. It's waiting until you add water. Then you pick up the proton, and then you just get an alcohol. But when the molecule, the carbonyl, when the carbonyl has a leaving group like this, initial delivery is the same thing. It makes a tetracarbonyl that brings oxygen electron pairs to goes up. So we got tetrahedral intermediates. And up to this part, it's almost same thing. But because we have a leaving groups, what happened was now this comes back and kick the leaving groups out. And that way, you get the ketone And then ketone is not safe under this Grignard. Grignard can react further because the Grignard is even easier to react with the ketone than the ester. So the products of the first Grignard even becomes a more reactive to the Grignard. So that makes it happen. I mean, then second methyl groups is attacked, the carbonyl of the ketone, and we get an alkoxy groups, and then there's nothing can happen because there's no living groups. It waits until you add the water, so you pick up the proton, and then you get the alcohol. But the difference is you are adding two Grignard reagents in the end to the ester, and then you get the tertiary alcohol. So this was something that we discussed many times in OChem 1, just to make sure that not all carbonyl react the same way with the Grignard. When there were living groups like this, ester is have a living group like this. Also, the acid chloride works same way. Even chlorine is going to be better living group. So we expect that it will be really reacting twice with the Grignard. So that's something that I really want you to remember. Sodium borohydride, lithium aluminum hydride, sodium borohydride, right? That the selectivity was something we discussed many times. Let's say you have a ester and the ketone together, then if you treat that with a sodium borohydride can only react with the aldehyde ketone. So that means it can only reduce this one's only. So that will be only one get reduced, and then ester will be just intact. But the lithium aluminum hydride will basically reduce all of this. It attacks that one, it attacks this one. It's just too powerful. So this one is going to be this, but the ester side is almost same thing. Hydride makes an attack, this goes up, right? Then what happened was it's almost same as ester reacting with the Grignard twice. This one kicked this methoxy groups out. I mean, it was used stay O minus in the beginning. In the meantime, then it generate the ketone. I mean aldehyde because we add a hydride, not the. But aldehyde is not safe under the such a strong reductive condition. So lithium aluminum hydride, if we add it there, it can react again. So that's make another hydride is added there. Then 2 hydride is added. This 2 hydrogen is added from the 2 lithium aluminum hydride, and obviously this hydrogen is also added by the lithium aluminum hydride too. And then now there's nothing can happen then when you put into the water, all of the oxygen get the proton, then it will be just alcohol. I mean, all of them turns out to be an alcohol, but ester basically react twice with the lithium aluminum hydride. So this is a type of selectivity I really want you to remember. Okay, so I think I sort of like briefly, but at least going over several reactions and some of the things that you need to remember in the OChem 1. And then what I'm going to go is sort of like those are last problems that I uploaded it is having a sort of like synthetic questions on something like this. So let me write it down, the question here first. The question is, you need to make this molecule, but all you can use is this. Ethanol is the only thing that you can use, but in the end, you have to make that. So this is the only source. I mean, obviously, this is an ester. Sometimes you have to think backward. If you may go forward, but you have to think about which parts that you need. Ester can be formed by two different reagents. One, you need a carboxylic acid like this, and then you need an alcohol like this. If you have those two together and then add a strong acid, then you can make an ester. That part is just same as that part. So we can identify the ethanol can be used as an alcohol for the esterification, but we don't have the acetic acid there. So then we need to think about how we can prepare acetic acid from the ethanol, right? The, something that you need to you see is that this is a basically this alcohol has a two carbon, right? And then this acetic acid also have a two carbon. So we basically we can simply we don't have to add any more carbon. We only need to convert alcohol to the carboxylic acid. So how can we convert alcohol to carboxylic acid? We basically need to oxidize it. But what reagent do we need to use? I mean, for the oxidation reaction, we talked about like a PCC or like a PDC, or even we talked about Collins, right? Or we even talked about Swan oxidation. But those things are, if you're using to the alcohol, then any of these things will basically makes an aldehyde because it's a primary alcohol. But we need a carboxylic acid, so something more stronger. So the one of the reagents is a chromic acid, right? So the chrome trioxide and then sulfuric acid and then dilute it into the acetone. That's basically Jones reagent, or you can use just dichromate. And then this will basically, you get the carboxylic acid. And then once you make the carboxylic acid, adding the alcohol due to the Fischer esterification, then you can get the products prepared. So this is the sort of things what you need to do. The first one was not too difficult to figure that out. Now, moving on to the second part of not next one after that is sort of like you have this, but you still have to make the same thing. Then then this one is a sort of like a little bit difficult because of, in the beginning you have four carbons in the structures. But once again, this is an ester. I mean, we have an oxygen in between. If we got four carbon there, but it's sort of like a two carbon, and then we got oxygen and two carbon. So even though we got the same number of carbon, we cannot basically do that. I mean, convert this to that in a simply. We have to break this thing that in a half so we can get the two carbon pieces. What is needed to make it happen the same way? We need the carboxylic acid, right? We need an alcohol, and then we can do the Fischer esterifications. Then how are we going to get the carboxylic acid? How are we going to get the alcohol? Right? That is a sort of things we can do here. Double bonds can be break down depending on how you do it. You may be able to just like a permanganate, if you do the permanganate, and then you do that in the hot and concentrated condition, then this is both sides is a symmetrical molecules. You get the carboxylic acid, two carboxylic acid. So this is there. So you can already use that one. But we don't have this one. So what you can do, you can reduce it. Carboxylic acid can be reduced to an alcohol by treating the lithium aluminum hydride. If you treat that with the sodium borohydride, that's not strong enough. Nothing can happen. But lithium aluminum hydride will reduce the carboxylic acid, the primary alcohol. Then we can do this. What if you didn't use that? What if you decide to use ozonolysis? So you try to ozone and then to the reductive walk up there. Then this is a singly both singly substituted. You got the two aldehyde. The one of these aldehyde, the other is an aldehyde. Then you need to basically convert both of them. One of these has to be oxidized to the carboxylic acid. And then what reagent would you use? I would say, the chromic acid, because if you're doing, it's already an aldehyde, you decide to put like a PCC or any of those chrome trioxide with a pyridine, then it will not react any further because those things can only oxidize to an aldehyde. So you need a stronger reagents like the chrome trioxide, CrO3, and sulfuric acid. This is sort of like overkill. There are better reagents we can talk about later, but at least this Jones reagent works well. But this part we need to reduce the aldehyde to the primary alcohol. Because it's an aldehyde, you can use a lithium aluminum hydride, but you can also use a sodium borohydride too. because aldehyde can react with the uh, sodium borohydride. It's much easier with the sodium borohydride because it's much safer. It's just the lithium aluminum hydride is too powerful. You just have to be careful using it. So this is sort of like trying to identify pieces to make it happen, and then think about how you're going to get those pieces from the reaction that you already know from the organic chemistry one. So this example, I think, is giving you an idea that you need to think about in a multiple different way. And now this question is becomes a kind of a little bit more harder. Now we have this, but you are need to make this. So this is a basically you got two carbon, but in the end we have to make a four carbon. So you can easily see that two carbon and then two carbon you add it together, then it will make a four carbon. Then how are we going to add it together? We have to make a carbon bonds, right? That's something that you have to keep in mind. Do we know any reaction that you can use to make a carbon bonds, right? So first of all, this alcohol is something that you need to use. Um, you have to think about maybe this part could be this, but then if you think about that could be the carboxylic acid, then it will not happen because whatever the reaction we use, then the oxygen will always going to remaining. So this is not the way to go. So what you need to think about is sort of like we need to sometimes walk backward. If it's when things are not quite clear, the forward reaction is hard to imagine how things can happen. Then often cases you try to do the back track, back step from the products. Then it may give you the better ideas. Sometimes it give you this. It makes you see things that you weren't able to see in the beginning. So let me tell you what I'm talking about. This is what we need to get. But think about don't just trying to think from there. Think from here. What if you have anything? Then how you gonna make that? So I'm gonna give you an idea that if it's a ketone, right? So one of the possibility is if you have an alcohol, if you have this, and I think I can make that. So that is definitely possibility, right? Then there could be another possibility there too, but this is definitely one of the choices. Then the question goes, and then how am I gonna? What else do I need to make this happen? And then you need to think about this is an alcohol, right? So that means maybe I can add water to or double bonds like this. Then if I add the water, then I can make this. So that could be another choices. Then then the question still goes, how am I going to make these double bonds there? So, I mean, it can keep going, but if we need to able to connect to the starting material at some points. So this could be the one way. Another way is um, we what if we are having like an aldehyde here, and then I'm adding this part as a nucleophile, like a ethyl magnesium bromide. And if I have that, this ethyl groups makes an attack, and then it's going to make this an alcohol. So that is a possibility. If you have this, and then you can make it happen. So this is sort of like already breaking things down in two different ways. So this is an alcohol. How are we going to make an aldehyde from the primary alcohol? Well, that is something that we talked about. You shouldn't use a Jones. If you're using a Jones, here, then you will get the carboxylic acid. So it cannot be the Jones. So what you need to use is something like a PCC, right? Or if you can use a PDC if you want to. You can use a Collins, or you can use a Swan oxidation. Then you can make an aldehyde from this. Then the question goes, how am I going to get this ethyl magnesium bromide from the ethanol? Well, you need to think about what you need to make an ethyl magnesium bromide. You need to have a ethyl bromide there. Then can I do this? Ethanol to the ethyl bromide, right? All you need to do, you need to replace hydroxyl groups with a bromine. Do I know any reagent for that? And then I guess we recently learned something called the PbL3, right? Then you can convert hydroxyl groups to the bromine, and then that way you can actually make the Grignard reagent by treating the magnesium metal. So this is a I mean, there's no numbers needed right now. And then you do the PC oxidation of that to make an aldehyde. You can make those two react and then make this happen, right? So this is a sort of like a way to do it. Then is there any other way? I mean, is there could be any other way to make it happen? Well, we haven't learned that yet, but this is also a viable route. We can do this. I need to introduce some of the reaction that we're going to discuss in the part two. So that's why I'm sort of like not trying to do that right now. But this is also viable route. We can make this from like aldehyde, and then we need some other reagents from there. There's something called the Vidic reactions we're going to learn later in the next after test one. So this route is also possible. It can also come from there. I mean, right now I'm trying to limit it down to the only the reaction that we only talked about so far. So this first route is sort of a giving there, but this is also viable route, and then we can talk about that later. Um, I guess it's sort of like a time there. The only things that I like to point about is uh, sometimes when you have to accomplish a synthetic goal like this, then many times you can you can easily figure out from the beginning to the end. But there are some situations that these forward steps it's not that easy to figure out. Then I would suggest that you think backward, starting from here. How am I going to make this? But in order to make that, what sort of things do I need? Sort of like a recognizing, like a one step before, what should I have that? I mean, if you can figure that out, then sort of you step back again, and then if that could be that end. Right now, we don't know how to use that, so how to make that even. So that's why then it's sort of like a dead end, and then we have to go back and think about is there any other way to break this molecule or change this molecule. As I said, we recognize this bond can be made by the Grignard. Then that will allow us to find the pieces that can be prepared, the starting materials and goes and things like that. So this is a actually we still can do it. Yeah, I just realized that. Okay, so let's as a last part, let me solve this question and then give you an idea of the what else we can do. So this is a sort of things. Now, since you need the many reactions, sometimes I mean, obviously, if you know the Vedic reaction, you can do this, but this can be prepared some other way. So let me give you an idea. So what is another way is um, we already talked about this can be here, right? This can be done. You can prepare the aldehyde like this aldehyde from the ethanol by the same way. And then to this, what you need to use is actually it's going to go there directly. Is that you need to use the sort of like not the I mean this ethyl magnesium bromide, right? They're not directly. Wait a minute, that's the same thing I just talked about. Okay, I'm sorry. I was thinking something else. Now I forgot my train of thought. Uh,
Using the ethyl magnesium bromide would just be a Grignard reaction, right?
yeah, yeah, that's a greener reaction. I was thinking something else, and then somehow I forgot the hmm, something that how am I going to double bonds there, right? Oh, I mean, there's a variety of different way. I mean, I just have to want to think about how we're gonna get to this part so we can actually go back up there. Um, okay, maybe not the reaction that not with the reaction that only the reaction that we know so far. I mean, to make it happen, the Grignard is definitely, I mean, Wittig reaction is definitely the choice, but this will be introduced next part. So without it, how am I going to go get there? I mean, first of oxidation to an aldehyde, but then it's going to be the same thing. So I guess without using any of the reaction that we haven't talked about yet, this is a probably only route possible. Um, Another way could be using the Gilman's reagents, but that also need some reaction that we haven't talked about it yet. Or, oh, I think we have talked about it. Okay, so let's talk about this one. So I don't know whether you remember the Gilman's reagents. Let me just clear it out. Oops, what was it? It was ethanol. Okay, ethanols, and then we need to make this one. So as you notice that we have to make a two parts. So I'm thinking about cutting there. And then in order to make it happen, what we need is something like this. Um, I don't know whether we learned this thing or not. This has to be the organocopper reagents. And then they will produce that. Did we learn this in OChem 1? Do you
You
remember?
said it was a Gilman reagent?
Yeah,
I
diethyl cuprate.
I've never heard of it. At least I didn't learn it in OChem 1, but I don't know.
Yeah, I mean that I'm maybe confused by the class I'm teaching in the graduate course. We definitely talk about that in the graduate course. But let me introduce the Gilman's reagents. Gilman's reagents is actually very powerful reagents. So since we maybe some of you may not know, let me introduce what it is. The like if you have a like a ethyl bromide, and then what you can do, treat the lithium metal, then you can make organolithium like this. To that, you need to just add a cuprous iodide. Just and then this becomes two ethyl groups and then bound to the copper, and then lithium is a basic counter cation. So this is a Gilman's reagents. So if I just write it down here, the copper have a two ethyl groups and then lithium's there. What this one does, it can transfer these ethyl groups in a very different molecule. Like let's say you got the cyclohexyl bromide there, then this bromine can be replaced by these ethyl groups. You can basically make this one goes in. It's almost like an SN2 reaction, but it is not an SN2 reaction. Funny thing is, if you have a something like um, halogen and benzene, you will never be able to replace that by regular SN2 reaction because if you keep expecting that cyanide makes an attack and kicks it out, this will never happen on benzene. This will never happen because this is sp2 carbon. But this copper reagent is done go differently. And then even the halogens on benzene, you can replace and makes like this. So maybe what I was thinking is if you have a this one, and then if you have this ethyl diethyl cuprate, then you can prepare. Oh no, that was not it. Sorry. Yeah, the in order to make this one happen, yeah, that was not it. I'm sorry, I'm confused. Gee, but anyway, this Gilman's reagent could be very useful because it just makes a carbon and carbon bond, right? It not even just this type of sp3 carbon. It can also make it happen even to an sp2 carbon, which is a impossible with an SN2 reaction. But this diethyl cuprate replace that. What else Gilman's reagent does? It also replaced the halogen on the acid chloride. So acid chloride, then you got the diethyl cuprate there. These ethyl groups is replacing the chlorine, and then you get to form this ketone. And then where these ones are coming from, that's coming from the first of all, you need to oxidize to the carboxylic acid. That would be the Jones reagents. And then in order to convert the hydroxyl groups to chloride, you can simply use a thionyl chloride we discussed in the class. I mean, we only talked about alcohol to the chlorine, but at least the carboxylic acid OH can be replaced the same way. And then this dielectric cuprate, where this one coming from, is coming from the here. So that means that you have to use like a PBl3. Then you get this one formed, and then you may have to make a dielectric cuprate, which is a Gilman reagent, and then now these two combined together will make it happen. I was not quite sure that whether we learned this thing in OChem 1, but I guess you might be right. Maybe we haven't learned it yet. Anyway, so this is another route. It's kind of a more complicated way than what we discussed, but the organic synthesis, there could be a multiple different route, and there could be several different answers possible, even the right answer. But some route may be more reasonable than the others. So those things are something that we need to consider. But now this type of synthetic question, maybe there's different people can come up with the different answers, and then we're gonna count on it when we look at the answers anyway. And so I guess I was trying to go over some of the reaction that we discussed in OChem 1, and then trying to give you an idea that how to solve these multi-step synthesis, how to design the multi-step synthesis problems using those homework problems. But this sort of like giving you an idea that if you're not really easy to following me up here right now, then you probably need to step up and study more for the reaction that we discussed already in the previous courses, and also the one that we already discussed in the chapter 11. And these are something that you're gonna need in even the next part. When we're discussing the ketones and aldehyde, the carbonyl chemistry, we're still gonna talk about alcohol, all the same nucleophile, similar types of reaction with the reduction with the lithium aluminum hydrides, with the borohydride, it all goes in. And then so I'm definitely sure that all of these reactions that we talked about today, you really need to know, not only for the test 1, but also for the test 2. Anyway, thanks for being with me today, and I hope that this snow day, at least we have a chance to talk about those reactions that covered in the previous courses. So hopefully this help you for the remaining part of the OChem 2. Thanks, and then I'll see
Definitely.
you on next Tuesday, right?
Sounds great. Thank you very much. Yeah.
Sure. Have a
Have
good
a good
day.
one.